the European Place for Molecular Research (CERN), is disclosing details of a new atom smasher today. Something multiple times bigger and twice as deep. It has found 3 new particles that could help us understand how our universe was born and what its future looks like. Scientists at CERN have just unveiled findings that turn our understanding of the universe on its head. Beneath the surface of their historic experiments lies a world of particles and forces so strange they could be straight out of science fiction. From potential gateways to other dimensions to particles that challenge the very foundations of reality. What strange mysteries are concealed inside these experiments? Let's dive into the world of CERN and unravel the truths that could redefine our universe. The gateway to new dimensions. A wormhole could hypothetically appear out of nowhere in the sky. And the reason would be the groundbreaking experiments conducted at CERN, home of the Large Hadron Collider, LHC. The LHC is the world's largest and most powerful atom smasher, located near Geneva, straddling the border between Switzerland and France. There are secrets about this extraordinary organization that the world doesn't know. Secrets that could potentially change how we view physics and the universe. CERN, the European Organization for Nuclear Research, operates this gigantic scientific instrument, which spans over 27 kilometers and sits deep underground. The primary function of the Large Hadron Collider is to allow physicists to test predictions of various theories of particle physics. This includes the high-profile examination of the Standard Model of Particle Physics, which helps us understand the fundamental building blocks of the universe. At its core, the Large Hadron Collider works by accelerating protons to nearly the speed of light before smashing them together. These collisions produce a cascade of new particles, which scientists study to gain insights into the laws of nature. It was through such experiments that the Higgs boson, often referred to as the God particle, was discovered in 2012. This discovery confirmed how particles acquire mass and was a pivotal moment in particle physics. The experiments conducted at the Large Hadron Collider are essential for understanding phenomena that occur under extreme conditions, similar to those shortly after the Big Bang. The data gathered can reveal more about how the universe began, evolved, and the fundamental constituents of matter. This makes the Large Hadron Collider a key player in potentially uncovering new dimensions of reality. Dimensions that could explain mysteries surrounding dark matter and the fundamental forces of nature. Concerns and safety. Such advanced experimentation at CERN doesn't come without concerns. Some speculate about high-energy tests creating black holes or strange matter that could pose risks to Earth. However, CERN assures that all safety measures are met, and the scientific community closely monitors these experiments. Studies and theoretical models confirm that any dangerous scenarios are highly unlikely. Through its ongoing research and discoveries, CERN helps us better understand the universe and showcases the incredible power of human creativity and collaboration in the pursuit of knowledge. Unveiling the LHC. Humanity's modern wonder. The Large Hadron Collider at CERN isn't just an impressive piece of technology. It is a marvel of modern science and engineering. Situated beneath the Swiss-French border, the massive collider runs through a 27-kilometer-long tunnel, reaching depths of 175 meters underground. This makes it the largest particle collider in the world and one of the most critical instruments in the field of particle physics. The structure of the Large Hadron Collider is designed to handle experiments of unprecedented scale. The main ring of the collider, housed in a tunnel with a diameter of 3.8 meters, contains 2 parallel beam pipes. Each pipe directs protons in opposite directions, accelerated by a series of superconducting magnets. These magnets are crucial for maintaining the path of the protons, bending their trajectory at speeds close to the speed of light. Surrounding the beam pipes are layers of cooling systems that maintain a temperature colder than space, necessary to keep the superconducting magnets at their required operating temperature. The scale of the Large Hadron Collider is further highlighted by its use of thousands of magnets, including 1,232 dipole magnets to bend the beams and 392 quadrupole magnets to focus them. The largest and most powerful superconducting magnets used are 15 meters long and weigh 35 tons each, demonstrating the immense physical scale and technological ambition behind the Large Hadron Collider. Probing the universe's secrets. The primary purpose of the Large Hadron Collider is to explore the fundamentals of the universe by observing the smallest components of matter. By accelerating particles to nearly the speed of light and then colliding them, the Large Hadron Collider allows physicists to study the resulting particles produced during these collisions. This process helps test and expand our understanding of the Standard Model of particle physics, the current best description of the subatomic world. One of the critical objectives of the Collider's experiments is to unravel the mysteries of the Higgs boson. Its discovery at CERN in 2012 confirmed theories about how particles gain mass. The Large Hadron Collider also investigates other fundamental particles and forces, aiming to answer essential questions like the existence of dark matter and the nature of the universe shortly after the Big Bang. Moreover, the Collider seeks to confirm the existence of new particles predicted by theoretical physics but not yet observed. These experiments are vital for potentially discovering new physics beyond the Standard Model, including supersymmetry and dimensions beyond the familiar three spatial dimensions. A vision of global collaboration. The vision behind the Large Hadron Collider is not just to understand the universe's building blocks but to foster global collaboration. With thousands of scientists from over 100 countries working together, the Large Hadron Collider is proof of international cooperation in the quest for knowledge. Through this massive and complex apparatus, humanity continues to push the boundaries of what is known and venture into the quantum realm. How does the Large Hadron Collider work? At the heart of CERN's research facilities, the Large Hadron Collider functions as a powerful microscope into the quantum realm, allowing scientists to observe and study the fundamental particles that make up everything in the universe. The process of particle acceleration and collision is key to examining the foundations of physics. Inside the collider, two high-energy particle beams travel at nearly the speed of light before they are made to collide. These beams travel within ultra-high vacuum tubes, simulating the conditions of space. Superconducting electromagnets, chilled to temperatures colder than space, guide and focus the beams to designated collision points along the tunnel. These beams cross at extreme speeds, smashing particles together with immense energy. The collisions produce a variety of subatomic particles, some of which are highly unstable and exist only for fractions of a second. To detect and analyze the byproducts of these collisions, the Large Hadron Collider is equipped with enormous detectors, ATLAS, CMS, ALICE, and LHCb, each designed for specific types of research. These detectors capture data about the particles, including their mass, charge, and momentum. This data helps physicists test predictions of particle physics theories, including the Standard Model, and explore particles and forces that govern the universe. Groundbreaking discoveries. One of the most significant discoveries at the Large Hadron Collider was the confirmation of the Higgs boson in 2012, an event often called a once-in-a-lifetime achievement. This discovery validated the mechanism by which particles gain mass, a central component of the Standard Model. Beyond the Higgs boson, the Collider continues to investigate other fundamental questions. These include the nature of dark matter, the mysterious substance that makes up about 27% of the universe's mass and energy, and the forces that govern the behavior of matter at its most basic level. The Large Hadron Collider has also detected new particles and phenomena, some of which hint at physics beyond the Standard Model. These findings open the door to groundbreaking theories, such as supersymmetry, which proposes that every particle has a heavier superpartner, and the existence of dimensions beyond the familiar three-dimensional space. The future of CERN and the LHC. As the Large Hadron Collider continues its experiments, CERN is already planning upgrades to extend its capabilities. The High Luminosity LHC (HLLHC) project aims to significantly increase the Collider's data collection capacity, allowing for even more detailed studies of rare particle interactions. Looking further ahead, CERN has proposed the development of an even larger particle accelerator, known as the Future Circular Collider (FCC). With a planned circumference of 100 kilometers, this next-generation collider would dwarf the current LHC and push the boundaries of energy and precision in particle physics. Pushing the frontiers of knowledge. The work at CERN exemplifies humanity's relentless pursuit of understanding the universe. Through its groundbreaking experiments, the Large Hadron Collider has not only deepened our understanding of the fundamental forces and particles that make up reality but has also inspired a new generation of scientists and engineers. With every discovery, The LHC brings us closer to answering some of the most profound questions about the origins and fate of the universe. Could new dimensions exist? What is the nature of dark matter? How did the universe begin? And what will its ultimate destiny be? These questions may one day find answers through the continued work at CERN. The collider was the revelation of the Higgs boson in 2012. This particle, sometimes alluded to as the God particle, is critical because it provides evidence for the Higgs field, which is responsible for giving mass to elementary particles. The existence of the Higgs boson was predicted by the Standard Model, and its discovery was a monumental achievement, confirming long-standing theoretical predictions. Beyond the Higgs boson, the Large Hadron Collider has also been instrumental in discovering a range of other particles. For example, the collider has provided evidence for the existence of pentaquarks and confirmed the presence of tetraquarks, particles made up of 5 and 4 quarks, respectively, which had not been observed before. These discoveries expand our understanding of hadronic matter, which is composed of phenomena bound together by the strong nuclear force, the force that holds the nuclei of atoms together. These findings demonstrate the predictive power of the Standard Model and also open new avenues of research in particle physics, offering insights into the behavior of matter under extreme conditions, such as those shortly after the Big Bang. Theoretical risks. Science or science fiction. As the capabilities of the Large Hadron Collider expand, so do theories about its potential dangers. Two of the most discussed hypothetical risks associated with the collider are the creation of strangelets and the potential formation of miniature black holes. These scenarios have captured both public imagination and scientific scrutiny. Strangelets are a theoretical form of matter that is more stable than normal matter. The hypothesis suggests that strangelets could convert any matter they come into contact with into strange matter. The fear is that if strangelets were produced during particle collisions at the Large Hadron Collider, they could potentially trigger a catastrophic chain reaction, converting all matter on Earth into strange matter. However, extensive research and safety assessments conducted by CERN and the global scientific community have addressed these concerns. Studies have shown that if strangelets could indeed exist and were produced at the collider, they would most likely be highly unstable and decay too quickly to cause any transformation of Earth's matter. Additionally, cosmic rays, high-energy particles from space, regularly hit the Earth with energies much higher than those produced by the collider without generating strangelets. This natural experiment suggests that strangelets are not a credible threat. Miniature black holes are another speculative risk. According to some theoretical models, the high-energy collisions inside the Large Hadron Collider could generate tiny black holes that would evaporate quickly due to a process known as Hawking radiation, named after physicist Stephen Hawking. Experts agree that if miniature black holes were ever created at the collider, they would pose no threat. First, such black holes would be minuscule and short-lived, vanishing before they could interact with surrounding matter. Second, the energies involved in collider impacts, though immense by human standards, are still significantly lower than those of cosmic ray collisions that occur naturally. Since no dangerous miniature black holes have been observed from cosmic ray interactions, it is highly unlikely that the collider would produce any harmful effects. CERN, along with independent committees, conducts rigorous safety reviews to ensure that the experiments conducted at the collider pose no danger to humanity or the planet. These reviews incorporate theoretical analyses, experimental data, and safety guidelines to address any potential risks. While the theoretical risks often sound more like science fiction than plausible scientific outcomes, the scientific consensus, based on extensive research and natural cosmic events, is that the experiments at the Large Hadron Collider are safe, and the potential risks are negligible. The most exciting experiments. One of the most captivating and unconventional experiments proposed at CERN is the search for magnetic monopoles. A magnetic monopole is a theoretical particle that is a magnet with only one pole, either a north pole or a south pole. Unlike ordinary magnets, which always have both poles, the existence of magnetic monopoles was predicted by physicist Paul Dirac in 1931. Dirac demonstrated that their existence would explain why electric charge is quantized, meaning it only comes in discrete amounts. Despite their theoretical significance, magnetic monopoles have never been observed. At the Large Hadron Collider, researchers are searching for evidence of these elusive particles. If discovered, magnetic monopoles would revolutionize our understanding of magnetic fields and could lead to significant advancements in technology, including new forms of energy storage and transmission. Additionally, their discovery would provide experimental evidence for grand unified theories and string theories, which attempt to explain all fundamental forces of nature within a single framework. Another rare experiment involves studying the potential existence of particles that could travel faster than the speed of light. According to Einstein's theory of relativity, the speed of light is the ultimate speed limit in the universe. However, some theoretical models suggest that particles called tachyons could exist, which would always move faster than light. Detecting tachyons would profoundly challenge our understanding of spacetime and causality. While most physicists are skeptical about their existence, the search for such particles at the collider demonstrates CERN's openness to exploring even the most speculative aspects of theoretical physics. The Large Hadron Collider also enables scientists to conduct experiments that replicate the conditions of the early universe immediately following the Big Bang. These high-energy collisions create a state of matter known as quark-gluon plasma, which existed only microseconds after the Big Bang. By studying this plasma, physicists hope to better understand how the universe evolved from its initial high-energy state into the complex and structured cosmos we observe today. Pushing the boundaries of knowledge. The ultimate objective of the Large Hadron Collider is to push the frontiers of human knowledge, unraveling the mysteries of the universe. By colliding particles at unprecedented energies, it allows scientists to explore the fundamental nature of matter and the forces governing the universe. This relentless pursuit of understanding reflects humanity's innate curiosity and desire to explore. The discoveries made at the Large Hadron Collider have profound implications for our understanding of the universe. By probing the smallest building blocks of matter and the fundamental forces at play, these experiments deepen our comprehension of the universe's origins, evolution, and ultimate fate. They offer insights into the very fabric of reality and address some of the most profound questions about existence. Moreover, the technological advancements and scientific breakthroughs resulting from the collider's research have practical applications beyond particle physics. The development of advanced detectors, computing systems, and data analysis techniques has contributed to progress in fields such as medicine, material science, and information technology. The Large Hadron Collider experiments also foster international collaboration and inspire a new generation of scientists. Researchers worldwide work together, sharing knowledge and expertise to unlock the universe's secrets. This global cooperation demonstrates the power of science to transcend borders and bring people together in the pursuit of understanding. In conclusion, the Large Hadron Collider is a cornerstone of modern physics, enabling groundbreaking discoveries and pushing the boundaries of what we know about the universe. Its experiments reveal the nature of fundamental particles, forces, and the origins of matter, providing invaluable insights into the mysteries of existence. Through its technological innovations and international collaborations, the Large Hadron Collider embodies the spirit of scientific inquiry and the boundless potential of human curiosity.